Okay, it's my privilege to introduce you to the members of our panel. Today we have Matias Turkulainen, Nerf Studio maintainer. If you missed the first part of the meetup, please look at the recording, which we're going to be releasing later. Matias did a presentation about Nerf Studio, and if you watch it, I promise you, you'll learn a whole lot about Nerf Studio, the program we all love, and if you don't love it yet, you will love it. Joining Matias is Michael Rubloff, who probably needs no introduction, but I'll do it anyway. Michael is the founder and managing editor of radiancefields.com, and his mission is to make advanced imaging accessible to creative professionals and innovate traditional image making practices. He is joined by Florent Poux. Florent is the founder and lead instructor at the 3D Geodata Academy. With over a decade of experience, he specializes in point cloud processing and the latest AI applications to 3D. Thank you all for joining us and spending this time with us. I think I'll kick off the discussion if that's okay, if you unmute. And my first question, anyone can grab it. It's actually from Felix. And Felix took a look at the Wikipedia article about Gaussian splatting, and it said that volume rendering technique that deals with the direct rendering of volume data. And it says this technique was originally introduced as splatting by Lee Westover in the early 1990s. And the question from Felix is, if it was developed in the early 1990s, why is it that just now many of us are becoming aware of it and it's generating this excitement? Does anyone want to grab that question?
Yeah, maybe I can answer it in some, at least from my own personal perspective. So the term splatting has been around for quite some time in computer graphics. It originated from people who were trying to render point cloud data. So talking about like the early 2000s, where researchers were generating like really accurate point cloud data with LiDAR scanners, and they would be colored, for example, like it would be points with colors and stuff like that. And what they wanted to do is they wanted to render like continuous surfaces, like images from the point data. And there's these series of papers by this, I think he's German, this Zwicker guy. Basically, he's like Zwicker et al. You'll see a lot of his papers about splatting, about volume rendering splatting, about EWA splatting and stuff like that. And these were like kind of forward algorithms where you start with the point data and you just generate nice looking continuous images from it. And they dealt with things like anti-aliasing, because it's point data. How do you like generate discrete pixels out of them that look nice and they're not aliased and stuff like that? But what was missing back then was the whole differentiable aspect of the splatting algorithm. So 3D Gaussian splatting, it doesn't introduce anything new algorithmically. It introduces just a new way of formulating the whole splatting process differentiably. So what was missing was really the GPU, PyTorch, AutoGrad. Well, it's not really AutoGrad. It's like the gradients are manually computed, but basically the optimization part was missing from the splatting, which lets you do like differentiable splatting instead of just forward splatting.
Okay, that makes a lot of sense. Michael or Florent, do you have anything to add to this? And I guess my sort of follow-up question, maybe to both of you, would be if you have any thoughts on this, I'd love to hear it. But also, you both have backgrounds in 3D. What led you to become interested in Gaussian splatting?
Yeah, if you want, I can kick off the things, Michael, and then I leave it to you. So first off, Matias, thanks a lot for the presentation. It was super nice, and I loved how you described yourself, just a kid on the internet. I mean, yeah, that's very humble from you, because you're doing a fantastic job, and of course with your team, this is fantastic, opening such technology is really a treat for a lot of people. So thanks a lot for what you're doing for the community and for the communities at large, because I guess in the audience we have people that come from VFX, surveying, geospatial industries, computer graphics, and autonomous driving. So it touches a lot of applications. So yeah, that was a forward just to thank you for what you've been doing. I perfectly agree with what you said. It's nothing new about Gaussian, especially. That's not 1990. 1990, it's Gaussian's fallback, very, very, very old concept. Applied to computer graphics for rendering stuff, it's 1990. I've played with it in 2008, I think 2008 for the first time, when I was trying to push out experiences displaying point cloud on the web, for example. I remember that we were trying to go around initializing techniques and splatting stuff, but it was really poor performances. So definitely, as with AI, having a lot of compute power helps a lot. Having very high level libraries like PyTorch, TensorFlows, and Keras and helps tremendously push the research community. So yeah, super cool stuff there, and it's very active. For my personal interest is mostly how can 3D point clouds be useful, because it's very close to sensory raw output. So it's very nice if we can try to have decision-making scenario closer to this representation. Gaussian splatting is one way to represent data. Now I think we'll see things how to interact with it much better, how you can build things really using spherical harmonics or things like this would be super interesting. What we saw on 4D Gaussian splatting is also super interesting. So this is what makes me, let's say, super interested in Gaussian splatting and NERF, the way to represent point cloud data so that we don't have necessarily to go through meshing stages. But yeah, we are not there yet, especially in VFX and gaming and computer graphics. So let's see how things move on. So up to you, Michael, if you have things to add.
Yeah, so I think for me, I can kind of tackle the latter half of Mike's question is just, how did I get into the world of, Gaussian splatting? And for me, back in the early 2023, even late 2022, I'd started a website at the time, which was called neuralradiancefields.io. And essentially, the thing that I was trying to do was that I kept seeing a very large rate of progression in the technology and a lack of media coverage and being able to actually showcase what this technology can do. And so I had been cataloging, the progression of NERFs. And throughout the course of last year, I kind of realized that the larger category was really with the larger topic was really radiance fields. And, with the release of Gaussian splatting, the full title, I believe, is like 3D Gaussian splatting for real-time radiance field rendering or something of that nature. And so I decided to kind of expand the overarching topic into just generalized radiance fields, of which, Gaussian splatting falls under. But my primary interest was really taking a look at how do we create hyperreal 3D from standard 2D images. And that's one of the things that really got me excited about generalized radiance fields is that you don't need any specific type of camera. You don't need a LiDAR sensor. You really just need anything that's capable of creating a still 2D image. And from that, you're able to create hyperreal 3 and, now approaching 4D as well in a somewhat easier than it has been in the past. So that really just got me excited. And throughout the course of even this year, one of the things that I've been really excited about is, obviously you can visualize things in hyperreal 3D, but there's also just the baseline of what you can do with some of these methods. There's a lot more ways that you can extend it out for individualized business use cases, which is just really exciting to me.
Fantastic. So Michael, your website was probably the thing that got me into radiance fields. So like, and I think, your excitement for it is really contagious. And probably I came from it from maybe a somewhat similar angle, and that being a photojournalist, I wanted to see how 3D could be applied to photojournalism, and a lot of the traditional techniques like photogrammetry didn't really work the way I wanted them to work, and Gaussian splatting looked really promising. And then it was your website and the information I saw on it that made me think, oh wait, I could do this probably. And then gradually, you know, it happened. And now, right, flash forward to today, it feels like everyone's talking about Gaussian splatting, and there's posts on LinkedIn all the time. But so my question to you would be, have we gotten to the point where it's overhyped? Is, you know, is now Gaussian splatting the solution to every problem, but actually it's not, it's only the solution to a few problems? What do you think?
Yeah, it's an interesting question. And I think from what I've seen so far is that, you know, media and entertainment as an industry has kind of like embraced its potential application first, you know, in terms of using it for like virtual production or bringing it to just, yeah, more media related shoots. I think that we're starting to enter that point of, I don't want to say like reality, but, you know, we're being able to start to actually like think through like how things are going to be utilized. And we're starting to see more of an adoption now in e-commerce, for instance. And I kind of have seen that across startups to some of like the actually largest companies in the world have begun actually using Gaussian splatting to just host, you know, natively onto the web. So I think that we're just kind of entering in the period now where we're seeing the actual building phase of people who are beginning to implement the technology. So I kind of expect over the course of the next 6 months or so that we're going to see more and more companies emerge that are using it in various industries. I actually think it's going to branch out quite extensively. You know, another one that's really getting a lot of hype right now is self-driving or, you know, autonomous vehicles. We're really starting to see a lot. For instance, you see Wave just announced Prism 1, which is powered by 4D Gaussian splatting. And there's a few other ones. You know, Tesla's hiring right now for engineers that are, you know, familiarized in the space. There's a company called Zoox, Zoox, as well, that is also, you know, bringing some people on board. And I don't think it's going to be capped there. I think that there's going to be quite a lot of industries that use this technology, and the technology itself is going to also continue, you know, to get better. It's not like we have a firm understanding of where the ceiling is yet.
Yeah. Florent or Matias, do you have any thoughts on this? And I'll commit the sin of asking you to predict where this is going. I know that's a terrible question to ask you, but I've got to ask it because someone like me is non-technical, wants to hear from the technical experts. You know, what are the new use cases that are going to come, and where might we be going with this? So apologies in advance.
Yeah, no worries. Yeah, very tricky question. I can give some like two cents thoughts on it, let's say. But it's very important to understand, and Matias touched very briefly on it, that Gaussian splatting and nerves are just extending a step, usually from structure from motion. So you still need to have input images and have some kind of alignment, so pose estimation. And this highly depends on photogrammetric workflow, except you don't do anymore the dense matching where you take all images and you will match per pixel. Here you use a neural network in nerves or something else in Gaussian splatting. So it's really this part that is interesting, that pushes a lot toward rendering scenarios or visualization application. So this is all the industries that have a high need of better showcasing something, for example, they will be highly impacted. I think about, I don't know, if you buy things online, if there is a need or to better see a specific product, that will be super interesting. Like buying a car, buying anything, I think this is very nice. Fashion also. From my like field of expertise as far as application go, it's mostly geospatial. So in here, if you talk about construction, there is a high need or very, very big need to better visualize. The only thing is there will be a limit to what Gaussian splatting on Earth can do. If at any stage you need some kind of sound geometry, this is where it's not yet at the stage that you can move that to a proof of concept. You still need to have this extra layer of research that researchers are doing in various university and labs. So let's see how that is pushed out. You have some, I think, papers that push out mesh using this radiance fields that may prove better than classical meshing strategies. But yeah, still, this is the aspect before visualization that need to be addressed before we can see a huge progress in startup, I think.
Okay, I think related to the answer, you just spoke about, there's a question in the chat from David Heath, and it's actually a question to all three about, what's the greatest use case for Gaussian splatting that you see. But I'm interested in the second part of his question, which is about the level of accuracy. And it's my sort of layman's impression that Gaussian splatting doesn't achieve the kind of accuracy for, let's say, engineering pursuits that you might get with photogrammetry. Could you talk a little bit about that, about the level of accuracy in Gaussian splatting and what it can be used for, and whether there are any improvements coming?
Yeah, sure. And then I will leave the talk a bit to Matias and Michael, but it's very, very different, the representation of things from the geometric base. The geometric base is a point cloud. You just have a bunch of extra features on it, mainly spherical harmonics for Gaussian splatting, that will allow you to display point cloud in a certain way. But when we talk about accuracy, I guess it's accuracy on the geometry that we talk about here. And at the moment, Gaussian splatting doesn't do anything toward this aspect of thing. This is really related to the way you capture your data and the way you have a nice pose estimation, so mostly photogrammetry. You won't get benefits on accuracy by using Gaussian splatting. However, on the visualization side of things, rasterization and resolution, you may or you will have a much better experience with much fewer points than you will have in a classical photogrammetry where you need to have a lot of points to have something very nice. So this is a bit of a dichotomy, especially in industries where people are very, very vigilant on the accuracy side of things, because now it may seem like, oh wow, it's super accurate, but whenever you will want to take measurements, it's actually not the case. So there will be this fine line to adjust, I think, yeah.
Makes sense. Thanks. Michael or Matias, any thoughts?
Can you repeat the question again?
Sure. I mean, I guess we're having sort of a sort of wide-ranging discussion about use cases for Gaussian splatting and maybe some use cases that are emerging. And then the most recent question was a bit about accuracy. The accuracy of a like photogrammetry mesh versus a Gaussian splatting render of a scene.
Yeah. Maybe I can partially answer that question. Maybe not entirely fully, but what I'm interested in Gaussian splatting over, for example, the previous kind of method, which was NERF, is that Gaussian splatting allows for this sort of easier to store and more explicit representation. It can be pretty much stored as a point cloud file with some additional metadata to kind of handle the colors and the geometry of Gaussians. And this can be more easily shared and also viewed on like normal devices, like on your phone or on a web browser. Whereas the NERF-based method, where they were reliant on small neural networks, basically, and having a neural network requirement basically also means that you're relying on some other library like PyTorch, which is a very big dependency for a software project to kind of implement or something. For example, you can't just use PyTorch on most like CPU or low-end devices without like really big performance limitations. So 3D Gaussian splatting after the training is complete, it really allows for like, it's a new type of geometric representation that's a bit easier to deal with than NERF, and it's easier to kind of manipulate as well.
And I can answer the second half of that question in terms of some of the industries. I look at it as if you just look at it on a straight market value, you take a look at AEC or heavy industry manufacturing in terms of just pure value. I think that there's going to be quite a lot of use cases to do, one, just general visualization, but, kind of going back to what I was saying a little bit earlier is that visualization is also just like a baseline that you can build on top of too. So if you wanted to incorporate some kind of like semantics, for instance, or do some level of automation, I kind of view this as also being a bit of an inevitability that I think will also really help boost productivity levels across different organizations. And I kind of look at that as like a industry agnostic thing too. While I think it's going to impact like heavy industry and agriculture and travel and some of the other ones too, it's really, in my opinion, not going to be limited across just one or two.
Talk to me a little bit more about that. So when you say it will impact the efficiency of various industries, in what way do you see that happening?
Sure. So if I'll take like agriculture as a potential example. And if you were to fly a drone over like a agricultural field, for instance, and you wanted to know, every single, individual crop that needed to be visited by an actual person, you'd be able to use semantics, for instance, on top of a radiance field to then like actually ask it like, based on this field, which plants need attention by a human. And you can actually, save time rather than having someone walk through a field every single day and kind of like manually inspect things. And, one of the other ones too is just like, say, if you were in more in like the geospatial and you were doing, or say you're in a oil rig or something, and you're only doing maintenance every so often, it's not easy to get people to the oil rig. You could automate like a drone path, for instance, across that, and then actually, use that to query, like, does this site need someone to come out to visit? And again, I think you can extend this to quite a lot of places, but semantic-based automation and productivity, I think, is something that's really interesting to me.
Cool. Okay, that makes sense. Matias or Florent, you have any thoughts on this?
Yeah, I agree. Semantics for me, this is where, but it's not necessarily linked to Gaussian splatting semantics. It's more linked to the process that is underlying, because you can extract semantics on the imagery of your drone or an auto image and have the same GPT-like model that will send back the answer. Where I think what Michael's point is super interesting is indeed, whenever you will find a way to leverage the capacity or the capability that Gaussian splatting gives, this super nice way of getting, for example, reflections or simulating a bit the lighting. These are elements that are true limitation in other workflows, like photogrammetric workflows or on single image. And here you have this ability to get that as part of Gaussian splatting. So this is an extra cue that you can use for semantics application that can tell you, I don't know, here it's a mirror. So it's, yeah, you can use that for decision-making scenario. If you want to plan, I don't know, a library full of mirror, you want to count how many mirror you have or whatever. So, so this is, I think, where the big wins will come whenever semantics will be injected much, much more, so that we shorten a bit the workflow that we have with a lot of processing stages to just acquiring data with some sensors. The point cloud, having it, for example, sampled as Gaussian splatting and having that as a base for the semantic query and extraction. So yeah, I perfectly agree.
Yeah, and one additional one too, just to go back to the example of like Wave and autonomous driving, they're using it for, definitely visualization, but then they're getting significant value from simulation on top of that. And it's just another potential where you can simulate the real world in a significantly easier capacity. And, because of this, because of, Gaussian splatting, they're dropping the reliance on like LiDAR scanners as well. And they're really able just to use standard RGB images, which I think it's yet to really be appreciated fully about like how much is going to be possible from several different ways with this technology.
So can you I've heard a little bit about it, but I can't say I truly understand it. Can you talk to me a little bit about how Gaussian splatting is used for robotics simulations? Does that also require sort of physics or collision? I mean, how do they use it?
So I probably won't be able to go too deeply into this, but I know there are a couple of really interesting papers like Phys Gaussian, for instance, where you can pair it with physics libraries to like run simulations. So some of the crazy examples, like, in that paper, they show like jams kind of like spreading itself across a piece of toast, or things that, propellers spinning on a plane. And so you can kind of like take a look at some of those potential applications. I can't really go too deep into
Yeah.
this one, but there are the ability to incorporate real world physics to it.
Yeah. And then Florent, I just want to make sure that I understood your comment before. So when we were talking about semantics, you mentioned that semantics, it's not just for Gaussian splatting, right? That you can do semantic segmentation with photogrammetry, with all kinds of things. So what would be the differentiator with Gaussian splatting? That would be its ability to render things like shiny surfaces or reflective surfaces. Would that be the use case for Gaussian splatting with segmentation? I just want to make sure I understood that point you made.
Yeah, no, you're right, because it's a bit tricky. So I will try to be much more, let's say, high level. Essentially, we have to think of all that is linked with Gaussian splatting as a data processing challenge. And the data modality, the base data modality, is the point cloud. We just have a point cloud, XYZ, with a bunch of features. So in semantic segmentation approaches that are pushed every day or every 2 weeks, you have a new paper that will address point cloud, meshes, images, multiple modalities. It's just a matter of making sure that the feature that you pass to whichever architecture that you have are relevant and don't have any too much correlations initially. So for example, XYZ and RGB, that comes from 2 different sensors or 1 sensor, but they are a bit uncorrelated at a certain stage. And you can use that as the input to your network that will predict then if these points are part of a chair, table, I don't know, camera or whatever. With Gaussian splatting, you have on top these extra features that I learned, which are the spherical harmonics. And maybe they give some kind of hint about, to which class a certain element belong. I'm not sure. I didn't saw so many things because usually today the drive is really using deep learning, so it's kind of a black box, and you leave it to the architecture to learn the features for you. So in that sense, maybe that's a bit too supervised, that you create features with an architecture that will then pass to another architecture. Let's see how that behaves. You have some papers that does it. Seems like you have some kind of good metrics, but it's not state of the art yet. Usually you need to rely on point clouds to get this kind of semantic segmentation state of the art performances.
Okay. So you mentioned spherical harmonics, and for those of us in the audience who don't know what the hell spherical harmonics are, I'm one of them. Does anyone on the panel want to give a simple explanation of spherical harmonics and their significance in this field? Come on, who wants to answer that one? No? Matias? No? Michael? Yeah?
I can give a very superfluous answer.
Please do, because that's something I'm struggling with, and probably there are other people who are struggling with it.
I know it really helps impact so radiance fields have something called view-dependent effects, where essentially as you move your head around in a given space into the real world, you'll notice light moves and reflects, it shifts, and there's like an expectation on how that occurs. Radiance fields are able to model view-dependent effects, and spherical harmonics, greatly empower that in Gaussian splatting from my understanding. And the other thing that I was going to contribute is that they also make up a very large amount of the data in
I didn't know that.
So I think they make up something like 75% of the file size of traditional Gaussian splatting. And so it's been interesting because there have been some papers that have been looking to shift out spherical harmonics to other types of representations I've seen. But yeah, I would say, Matias, you probably has a better understanding than I do on it.
Yeah, I really don't. Spherical harmonics is like this big black box of math. It's like a rabbit hole if you want to really understand it. properly, I think it's quite difficult for new people trying to understand it. But from my basic understanding of spherical harmonics is that it's just an encoding system based on signal kind of Fourier analysis. Um, Spherical harmonics has different degrees, and the base degree is just like you can think of it as a constant value, which is your constant RGB value. But when you increase the degree, you're kind of incorporating more frequencies into the base RGB value. If you think about a view dependence, if you have a kind of like a sphere and it has a monotone RGB color, no matter what direction you look at it from, the color will always be the same.
Yeah.
But spherical harmonics are these Fourier features encoded on top of a sphere, basically. So when you look at it from a certain direction, the sphere, for example, you can get a different color from this direction than when you look at it from this direction. And the amount that the color changes from here and here, there's like explicit mathematical formulas for that, which are basically like sines and cosines. And when you increase the degree of your spherical harmonics, you increase like the waviness or like the frequency. So Gaussian splatting uses spherical harmonics to encode, to learn like the view dependent effects, and the learned effects are from the coefficients of the frequency encoding. So these are kind of like learnable parameters within the optimization that allows you to change your base color based on the viewing direction.
Fantastic. Thanks for that. That's amazing explanation that even I could grasp. And I see in the chat, Chris Hansen says he can answer this question. So maybe this could be an entire topic for another meetup. And Chris, I will be reaching out to you. A question popped up in the chat, which I think was linked to actually a question that came up, Matias, in your earlier talk that we didn't get time for. And that was about using Gaussian splatting to model really large environments. And so, and the question that came in this conversation, which was again from David Heath, which was, do we see any potential future integration with Google Maps and large scale reality representation? So maybe I could just sort of like break that out, and that is, could we talk a little bit about large scale Gaussian splatting, and could we talk about it specifically and how it relates to these data sets that people like Google have, and could those potentially be used to model the world with Gaussian splats? What are the challenges with that? What are the applications? What's the likelihood?
So I can kind of jump in on the Google Maps side. So interestingly, at least in in actually quite a few cities across the world, Google actually already directly supports NERFs inside for specific interior captures. So if like there's like a restaurant in Manhattan that you're looking at, a fair amount of them have NERFs directly embedded already into Google Maps. So I think that it's likely that we will see some continuation and expansion of that service from the Google team, going forwards, because they do still have a general immersive view, which is using the standard photogrammetry for more, landmarks across these individual cities. But there's been, I would say, a tremendous amount of research in the world of large scale, I guess radiance fields, where there's papers like there's like vast Gaussian and like city Gaussian. There's also a hierarchical one that came out from INRIA as well, somewhat recently. And then there's also papers like NERF XL, for instance, where essentially it allows you just to continue to scale out the size of the capture. So they actually created a 25-kilometer size NERF from that. I guess we'll see if that is able to be translated to Gaussian splatting in the future. But it shows the promise that, yeah, that 25-kilometer one, I think, is trained across 260,000 images, and it works. And so, we will see where this evolves to, but I wouldn't be surprised if it sooner than later.
That's amazing, because the ability to handle that many images and put them into a splat blows my mind. Florent, do you have any thoughts on large scale Gaussian splatting?
Yeah, sure. So I don't see that as an issue because it's already solved for the amount of images that you can align. So this is part of photogrammetry. And here it's mostly linked to the rendering pipeline to be solved, that you need to have some smart occlusion cooling, for example, or data structure that accelerate the way you display. But if I again pull that back to the point cloud and just consider that you have the same thing for Gaussian splatting, except you have like 35 more features, which are the spherical harmonics. It's just a matter for the rendering engine and pipeline to use that efficiently enough so that you can display large scale things. But on the point cloud side, for example, you can display unlimited amount of things. I've seen, and I've used like entire Australia, which is 140 terabytes of data streamed in real time. And you have like full country, the full world. It just, you create a structure, hierarchical structure. It's called an octree. And anytime you go deeper and deeper, you will just display some kind of cubes that go deeper and deeper. So I assume that, I'm not talking with Nerf, I'm talking with Gaussian splatting. You will be able to do the same thing, except that you may need to adjust a bit the structure, data structure, to handle better the amount of features that need to be used by the rendering engine. Yeah.
Cool. Yeah, I've encountered octrees for point cloud, so I didn't realize, okay, that makes total sense that's the way you would approach it. How is that similar? I mean, this is, forgive me, because this is probably totally different, but when I use, for instance, cesium ion to stream terrain, is that a similar process with the sort of pruning and octrees?
Yeah, exactly. It's just it's very simple. It's it's great engineering, basically, where you split up a square into some kind of sub entities. In the case of cesium, they use tiles called 3D tiles, right? And for the web mapping services, you have like WMS and things like this. And it's on 2D, so it's called a quad tree or an R tree, depending on how you move around things. You're just splitting up your data into little chunks that are manageable by your compute power, rendering pipeline, libraries, whichever tech stack is used behind you.
I'm looking through the chat, and this is maybe a somewhat related question from Animesh, and that is, what are the current bottlenecks in Gaussian splatting pipelines apart from being very large files? Are there any equivalent to JPEG compression algorithms for the final .ply file?
I can give somewhat of a high level answer to this. There actually been like a ton of work on condensing the size of the files now. So I'd say I think it's like around like 30 megabytes now that you can get them down to, and actually perhaps even smaller. I'm trying to remember for when I was doing the arrival spaces loading, I think it actually brought it down to like sub 20. But there's a lot of work that I think remains to be done, and they will probably get very tiny, I think, across all radiance fields, but I can't really go into how.
Okay. Does that make sense? I mean, so, when, at least at the moment, when I use most platforms, textured meshes are the first-class citizens, and Gaussian splats are this other feature that they've sort of half added. I was really glad to see in Guillermo's talk that Gaussian splatting seems to be really well integrated. But can any of the panel talk about, like, what are the barriers or the challenges to bringing sort of point cloud based objects into the current online worlds, which tend to be based around textured meshes, at least for the most part, because that's what's been the case, or sort of the standard for gaming and other fields in 3D.
Yeah, that's that's a fantastic question. It's very, very hard to answer, from my opinion. But basically it's about refining your oil to some degree, and the oil here would be point clouds. So it touches a bit on compression as well, or how much you need. Because if you take, I don't know, if I look at the screen behind you, you have a table. If you want to describe this table with classical meshing approach or such, or parametric modeling, this will be some equation that will define the cuboid for the top of the table and 4 cuboid for the legs, and that's it. And you have a way to have relationships between that. Now you want to do the same thing with point clouds. Basically, you have to have this sampled as points. So I don't know, you may have 100,000 points that describe your table. It's very, very raw. So it's very nice because it's a list of points, but you have no relationships and you have no compression at this stage. So it's a matter of trying to find the right balance into the number of points you need to describe a shape and what the industry is using as part of their tool set. Because right now, I mean, in geospatial industry, if you give a point cloud to a client that works for Paris City or something like this, it will be afraid and it will never contract anything with you anymore. So it's really this that will lock a bit. Like in AEC, you will take the point cloud, you will transform that into a BIM model or into a CAD floor plan or things like this. So if there is a way to maybe not go so far, but keep it at the point level and extract some kind of relationships between things and how you symbolize stuff, that will make a lot of sense. But I don't know if I was clear, but basically I think it's almost philosophical how you approach geometry and how we approach representation.
Okay, that makes sense. Let's see. Some questions that seem to be maybe callbacks to some of the stuff we've been talking about. Flavio asks, maybe this one's for you, Matias. Any plans to implement in Nerf Studio any method for addressing reconstruction of extremely large scenes with 3D technology like vast Gaussian, LOG, or hierarchical 3D Gaussian? If you're able to answer.
Yeah, it's an interesting question, and unfortunately, I'm not really able to answer it. I think, like Florent explained quite well, render larger and larger scenes, you probably need to add more optimization features to allow to do that. For example, you probably don't have to store all the Gaussians in the scene in memory at the same time. You can call them based on some visibility index and stuff like that. At the moment, Nerf Studio doesn't implement any of those sort of accelerated structures to allow that, but who knows, maybe in the future some keen open source developer or somebody creates a pull request and adds that as a feature.
Good answer. Yeah, do make a pull request and make it yourself. So here's a really interesting question for you, Matias, from Joel, and I think this is asked with a lot of love. What are the main things you think Nerf Studio is missing, and what would be most useful to improve?
Yeah, what can I say? Nerf Studio is amazing.
But if you could, I mean,
Yes.
granted, it is amazing. We all think it's amazing. But you know, if there's something like that you could like work on, like for me, you know, being non-scientist, being, you know, an end user, you know, I would love a GUI, you know, but that's just me. But how about for you? Like if you could like, you know, say, oh, I'm gonna have 6 months and I'm gonna work on a certain Nerf Studio feature. So let's just say, let's just make this you know, just a thought experiment. If you could just say, I'm going to go off in a corner and I'm going to build a feature for Nerf Studio, what might that, what's most exciting and interesting to you in what could be developed for Nerf Studio?
Yeah, I'll answer this completely from my own perspective.
Sure.
So there's a growing feature list of people asking for features and implementations and wishes and wants, but I think most of them cannot be like addressed. Personally, I just hope to take some time for myself to read some of these recent papers that have been coming out at, for example, NeurIPS and now at ECCV and stuff like that, that have kind of taken the vanilla 3D Gaussian splatting and incorporated some sort of small changes to it and shown some meaningful results in these research papers. So personally, I just hope that I can free some time for myself to read these papers, kind of understand their ideas, and then maybe try myself or to implement them into Gsplat. But yeah, it's quite busy these days, and yeah, I hope to find time for myself to also
Yeah,
do
no, I
this kind of
don't.
stuff.
We don't want to add to your burden. I mean, I think this is just the question was asked with a lot of love. Just sort of what what would you build?
One of the really cool features that actually just got put into Nerf Studio is there actually is now a Gradio interface, which is really, really easy to get set up. And it makes it is definitely the closest thing to like a full GUI for like picking out, you know, what settings or flags that you want to choose. So I highly recommend that people check that out, especially if they don't have like a technical background. I promise it's like very easy to get set up through the GitHub page, especially relative. If you've got Nerf Studio set up, this will be infinitely easier. And yeah, it's a great feature. So.
Cool. I'll definitely be checking that out. I'd seen it, you know, I'm sure you've mentioned it and others have mentioned it. I've just never gotten it set up for myself, but that sounds like a fantastic thing. I'm conscious that the panel has been with us for over 45 minutes, so they may be getting tired, but we do have more questions in the chat. Let's see. Okay, here we go. This is like a practical question. What's the best setup for capturing indoor environments, and how should uniform and large surfaces with low contrast be managed to achieve a high resolution result? So this is sort of a practical capture question.
I can answer this one.
Yeah, go for it.
Jump in. So one of the big things that not a lot of people know is that, you know, for standard photography, you know, it's made up of aperture, ISO, and shutter speed. In creating radiance fields, only two of them matter. ISO does not affect. Okay, I get balloons. ISO does not matter whatsoever, and so you can shoot. You know, the highest I've ever gone to shoot was 30,000, and it just pulls the noise out. And you know, for 30,000, it doesn't look terrible. Typically, I shoot somewhere between like maybe like 6,400 and 15,600, and there's no noise. So one, jack up the ISO as high as you need to get a fast shutter speed. Shutter speed is by far the most important part of creating a solid radiance field. If you are able to procure a wide angle lens, that also makes a huge difference in capturing. So fisheye lenses as of right now for Gaussian splatting isn't totally supported, but it's not necessarily like a hard cutoff. Like I have a 14mm fisheye lens that reconstructs completely fine with it. And typically the way that I suggest capturing indoor spaces is I try to, the more parallax that you're able to introduce in your capture is always greatly beneficial. So I try and move typically in a spiral outwards and then also try and repeat backwards. Again, that same loop. So I would do multiple passes, different angles, shoot wide angle, really fast shutter speed. ISO does not matter.
So that's exactly my experience as well. And I remember that I was at a shoot and I was asked to capture something and it was so dark. And I thought this is never going to work. And I looked at my images afterwards and they were the most noisy, disgusting mess you've ever seen. And I wouldn't have worked for photogrammetry, but it did work for Gaussian splatting. So my question is for Florent and Matias. Why? Why is it that you can feed in the most noisy, awful, disgusting images into Gaussian splatting, yet the resultant splat looks pretty good?
Yeah, it's the magic of Gaussian splatting, let's say. but the underlying is this. So Matias showed that briefly. You have Colmap is the most used one because it's open source as part of pose estimation and finding features. But you have other ones. So reality capture is now open if you do less than $1 million in revenue. So that's entirely free. They have a CLI as well, so you can use that to automate a bunch of the process. Metashape is also very good, but it's not free. And you have a lot, like Bentley has a very good one as well. So you have a lot to play around. OpenMVS. So this is the most fundamental point. This is the backend. And as Michael mentioned, if you have a good shot, it will work better. But in the case of the question, I think it was mentioning flat surfaces and very uniform colors. For now, there is no solution for that. You can project a pattern at a different frequency from your camera. You will not have that in the images, but you will have that in the pattern, and you use the pattern images to reconstruct your scene, and then you use the images to do the Gaussian splatting, and you merge both. That will work. I've seen that work. So this is one way to go around. The second way is pulling in a LiDAR sensor that will get the geometry and fusing after the pose of the sensor with the images, and you will get also a very nice representation. But as far as the quality of images, why it looks like it works for Gaussian splatting, this is, if you look at the geometry, so the point cloud, you will see that you have the same crappy one, but the Gaussian splatting will create huge like splats and that will feel like, okay, it's actually not so bad. But down the line, you still need ideally to have a very high shutter speed. The ISO, it depends on your camera, but the lowest, the better. If you really are into like metric application where you want sub-millimeter accuracy on things. And after, it's what Michael mentioned, you go in a room, which is a square, you go like this, you shoot the opposite direction. You move your camera at different set of point of perspective, like up and down, and looking like this, and you should have a very smooth thing. Yeah, I think I can stop there and leave it to Matias. Yeah.
I just wanted to follow up on, you mentioned two techniques for capturing featureless surfaces. So one was using LiDAR, which makes sense. So it's not using the optical. But for the other technique you mentioned, so was that you actually have two sets of images, one set of images with a pattern projected onto the surface, and then you do the initial maybe sparse cloud with that, and then you swap in the other set of pictures without the pattern? Is that the technique you're describing?
Yeah, it's I love this technique because it's a dirty trick, but it's actually super smart, and I've had the chance to use it as well for consulting the people that work on, if you saw the Star Wars Mandalorian stuff.
Sure.
They have huge screen behind that are projection, and that changes totally how they now move away from green screen and stuff like this. But what they do is that they have synchronized this with cameras. They don't have one camera, they have multiple cameras, and each of them shoot at a different frame rate. Like one will shoot at 30 frames per second, the other one at 60, and so on. And they will just have two images displayed depending on the position of the camera at a different frequency. So one camera only see a specific image and the other one only see another image. And this is how they give this impression and real-time actually shot. And this is the exact same technique that you can use where you synchronize. That's really not easy, yeah? Because synchronization, we talk about, like super high frame rate synchronization. So it's not easy to do, but if you can manage it to have it depending on your shutter speed, then you will be able to use both the set with the pattern and the set without the pattern for the visualization. Yeah. Okay, so just for the people that if it's a bit like playing around what I'm saying, next time you go in a plane, if it's a plane with this how was it called? The plane with the reactor. Forgot the English for that. The spinning stuff on the plane. So old plane, old school.
Oh,
propeller.
Propeller, yeah, thanks. So the propeller, if you take your phone and you shoot it at the propeller, you will see that you will have like a frame and it moves very slowly, or the wheels when you shoot a video on the autobahn, the wheels, the highway, sorry, you have the wheels that moves in very slowly. So this is exactly that. You just adjust your frame rate to pick up a certain signal that you will project. Yeah.
Okay. I've heard of the technique where, let's say you have an array of cameras that are static. Let's say you have 50 cameras. I've heard of a technique of, it sounds like similar to maybe the projection technique you're talking about, where they would maybe mark up the object, well, maybe shoot the scene and then mark up the scene and shoot it again and use the marked up set. But that only works if your cameras never move, right? But it wouldn't work for a single camera setup. There's another question, let's see, repeating a question from Anonymous. Right now, the biggest problem of 3D.js is the low quality in artifacts. All of them could be solved with adding more data for training. At the time, we see extremely cool results of video generations or in painting with diffusion models. So I guess it's obvious to combine both methods to increase the quality of 3D.js. Why don't we see something like that?
So, yeah, it's a very interesting phenomenon that's happening right now with diffusion and especially some of these video models. I think that we will see some, we're already starting to see some of them like from Luma AI, for instance. And I think that a lot of the people who are working on that are working on it in private, and that it will get very, very strong very quickly. And probably, yeah, I'm a little hesitant to give too much
Okay.
but I think
Very
it's
tantalizing answer there, but cool. We think we're kind of out of time here. We only have three minutes left. There was a question in the chat which has disappeared, and that was about 2DGS. Is that am I saying that correctly? The question has disappeared, so I don't know. Oh, here we go. No, the question is gone. Forget it. But isn't there a technique that I've seen recently? 2DGS? Does anyone want to talk about that? What is that, and why might we be interested in it?
Yeah, I think don't see the question anymore, but something about maybe like the pros and cons of 3DGS versus 2GS or something. And 2G Gaussian splatting is like was released as a research paper from Tübingen, and they were looking at like surface reconstruction with 3D Gaussian splatting. Although you have like a point cloud kind of at the underlying surface representation, you have these balls that are like three-dimensional, so this surface is not exactly defined. So what the 2D Gaussian splatting thing was, they like flattened the balls into disks, and then it was the same kind of rendering algorithm basically, where like a disk or the properties of a disk are like differentiable. It's something called like surfals. It's a different name for like 2D Gaussian splatting basically.
Okay.
And I guess the question was about the pros and cons.
Yeah.
I guess it's difficult to know at this stage, but if you're interested in surface reconstruction, I think that's probably the way to go, because a 2D planar like thing precisely defines a surface. For example, there's a like a closed form equation for getting, for example, transforming points from a pixel space into 3D space. If the surface is like a plane, there's a direct mapping of it. But then if it's a 3D Gaussian, it's quite like ill-defined. Like, where do you define the surface intersection with a 3D ball, for example? Do you cut some plane through it? Do you check like the density value at some certain point and stuff like that?
Mm.
But then I'm uncertain about like the visual quality of 2D Gaussian splatting. Does that bring something new on top of 3D Gaussian splatting? To me, it seems like it's quite equivalent when you're thinking about like the visual fidelity, like the rendering quality, like PSNR and stuff like that. It's super interesting, and definitely like I'm sure in upcoming conferences there will be more works that will use 2D Gaussian splatting as the rendering instead of 3D Gaussian splatting. We'll probably see some nice papers about kind of investigating which one is actually better.
Okay, fantastic. Now we're at time, so I just want to thank all of you for joining and sharing, so much of your expertise and your knowledge. So thank you, Michael. Thank you, Florent. Thank you, Matias. And a big thank you to Felix, who's not been on camera much, but is actually the anchor man who makes all of this happen by running the site and doing the webinar altogether. And thank you, everybody who's joined us here for this. It's been fantastic. And we really appreciate you joining us. And we hope that you will join us for the next one, which is going to be equally exciting and interesting. So thank you all for joining. It's been a real pleasure hosting this.